Hello, my name is Kevin Joback. I am with Molecular Knowledge Systems. Thank you very much for the opportunity to give this presentation. I will be talking about using computational tools for physical property estimation and solvent selection. My goal is to share with you some of our experiences and the approach we have been using in solvent selection projects for both product and process applications. Now, my presentation will cover most of the main aspects of selecting solvents: compilation of structural constraints, molecular structure constraints, compilation of physical property constraints. I will mention the evaluation of estimation techniques and the need to estimate physical properties. And we'll talk about the screening of candidate solvents. And the final step in any computational selection process is experimental verification, which I will not be talking about in this presentation. As a little background, Molecular Knowledge Systems provides computer software and consulting services. Our software focuses on physical property estimation and chemical product design, as does our consulting services. The work that I am presenting here was done using our Synapse software product, but what I'm going to talk about is not so much about our software tool, but really the information and the capabilities that are needed by any solvent selection tool. As such, I hope that the information I present here is applicable whether or not you use our tool, someone else's tool, or build your own tool, which can readily be done. So the solvent selection problem is actually a very straightforward problem. Given a database of solvents, we want to find which ones work well for a given application. Some of the things that might complicate the problem are that a lot of information is contained in a molecular structure. So it is very important that a software tool is able to understand and reason about molecular structures, in particular about molecular substructures. We will also often find that the data we need to make decisions is not available. Data such as the physical properties of solvents or the properties of the mixture of a candidate solvent and a product or process chemical. Sometimes we just have to make do with what we have. Other times, we are fortunate enough that we can use physical property estimation techniques to calculate values for these missing data. And finally, there are two aspects of the problem which are not always appreciated. At least, they were not something I appreciated previously. It is extremely important that whatever software tools we use, they have the ability to clearly document and archive the solvent selection process. By this, we simply mean that imagine 5 years from now, if someone asks you, how did you pick that solvent for the new cleaning solution we're selling? You can quickly find all the information that was used to make all the decisions in the selection process. So let's begin addressing each of these complications. During the solvent selection process, we will come across many constraints. Many of these constraints are of a molecular structure nature. For example, suppose we're selecting a solvent to be used in acidic conditions. One constraint we may add is to eliminate solvents containing unsaturated carbon bonds because of concerns they may degrade or react. Structural constraints often arise from interactions between solvents and process chemicals, solvents and impurities, solvents and materials of construction. Some materials of construction, particularly iron, copper, or aluminum, may actually promote or catalyze chemical reactions that may degrade solvents. Structural constraints need to consider operational conditions in which the solvent may be exposed to temperature extremes due to upsets or even just common usage. And one of the things that needs to be appreciated, particularly for process solvents, is that the types of reactions we're concerned about are not short-term reactions. Obviously, we're concerned about hazardous situations in which reactions may occur very quickly. But in most cases, we're concerned about reactions that may happen slowly, degrading the solvent over weeks or months. We've also found that there's not always good agreement or even a good understanding of what structural constraints should be imposed. So the best approach we can do is to thoroughly document our decision process. The best way we have found to document this decision process is by using groups, functional groups. For example, at times we may wish to eliminate solvents containing certain functional groups for environmental reasons. Solvents containing chlorine, bromine, or iodine are sometimes undesirable. Solvents containing certain functional groups may be eliminated because of stability or reactivity constraints. And nowadays, we are seeing more of what I call good neighbor constraints. Some solvents may be very good, non-hazardous, and safe for the environment, but they may smell bad. As we said, one of the very important tasks of a software tool is to document the decisions made during the solvent selection process. Using functional groups is a very robust and very easy method for performing such documentation. The second type of constraint that solvents must satisfy are physical property constraints. Now, many people and many software tools instantly say calculation of solubility is the main task needed when you select solvents. Solubility is obviously very important, but secondary properties also provide many constraints, and very often data values for these secondary properties or estimation techniques for these secondary properties are more available. Just consider the solvents used in a perfume or a ballpoint pen, or a liquid extraction process. We can see that in addition to solubility, properties such as evaporation rate, odor, viscosity, density, interfacial tension, vapor pressure, heat of vaporization, and heat capacity are also very important, and important enough to be used to eliminate candidate solvents. In addition, especially nowadays, constraints from regulations, the desire for solvents and products to be sustainable, acceptable to consumer preferences, and accountable, that means all degradation products are accounted for, are also critically important. So when we approach the solvent selection problem, in addition to just solubility, we look at many different physical properties to see if there are additional constraints. To help identify physical property constraints, we use a property category checklist. This checklist contains 14 physical property categories. Categories like phase equilibrium, which includes solubility, volatility, and the formation of azeotropes. Categories like rheology, which include viscosity and shear thinning behavior. Categories like sensory, which include skin feel, mouth feel, and odor. And when we look through these physical property categories, we must consider more than just the use of the solvent. This is what we typically focus on. How good is the solvent at cleaning or dissolving something? But we must also consider the entire life cycle, the raw materials and the source of the solvent, the manufacturing processes involved. How are the solvents mixed? How are the solvents blended? How are the solvents purified? Shipping and storage considerations often pose additional constraints, such as restrictions or extra costs due to flammability or the hazardous nature of a solvent. We must consider not only how the solvent will be used, but are there any ways the solvent might be abused? And finally, how is the solvent to be disposed or recycled? In the past, many solvents claimed to be biodegradable, but now it's more important to be able to say what chemicals they biodegrade into to ensure that no hazards are formed in the environment. In the news recently, we have seen how important the source of your solvent can be, as the number of recalls of hand sanitizer has increased, because the ethanol used also contains some methanol, which is not the case for the brand of hand sanitizer covered up in this image. So after we consider all these property categories, we should now have a long list of physical property constraints that we can add to our structural constraint. The problem is that when we look at the properties needed to evaluate these constraints, we may not always have values for them, and thus we must use physical property estimation techniques. And whenever we perform a new estimation, we should always determine which estimation techniques work best for the classes of chemicals being investigated. For example, the graph here shows the vapor pressure for furfural. Here we list 3 common vapor pressure estimation techniques. Although we have estimated the vapor pressure for furfural many times in the past, the particular temperature range of interest in this problem was different, so we wanted to estimate it again. Using software tools today, it is very easy to compare different estimation techniques. The Gomez-Nido-Thodos method is actually the one we would probably use by default for this molecule because it tends to work well for less volatile chemicals. However, surprisingly to us, the Lee-Kessler and the Ambrose-Walton method actually work better. So after this evaluation, we may need to update the estimated values in the database to use the newly selected estimation techniques. I've talked about some of the individual tasks needed to be performed by solvent selection software programs. Specifically, we talked about using groups to represent structural constraints and the compilation of constraints on many physical properties, evaluating estimation techniques, and using the selected estimation techniques to fill in the missing values in our database. Now I'll go through an example to show how these pieces fit together. The example I will use is the separation of furfural from water. Furfural is a popular bio-based chemical that has the potential for becoming a platform chemical for many new products. Unfortunately, even though the boiling point of furfural at 161.7 C is very different from the boiling point of water, as the graph shows here, furfural and water form an azeotrope. Thus, simple distillation will not work as a separation process. Typically, an extraction process is performed. So our goal is to find an extraction solvent that can separate furfural from water. In the process shown here, a furfural-water mixture enters the top of the extraction column, and the solvent enters the bottom. Hopefully, if we pick the appropriate solvent, an almost pure water stream will exit the bottom of the extraction column, and our furfural solvent mixture will end up at the top. This mixture will then be fed into a distillation column, in which we have chosen to take our furfural product off the bottom and recover our solvent off the top. So let's go through our solvent selection tasks. Our first task is to establish structural and property constraints. For this particular design, we have placed constraints on solvents containing chlorine, bromine, and iodine because of environmental concerns, unsaturated aliphatic carbons because of reactivity or stability concerns, and thiols and primary amines for reactivity and odor concerns. For physical property constraints, because we have decided to take our furfural product off the bottoms, our solvent must have a boiling point less than furfural's boiling point of 161.7 C. In addition, we have added a constraint that the melting point be less than -15 degrees C. This is simply to ensure our product remains liquid even when it is stored or being shipped in cold climates. This is not a constraint that is always imposed, but for us, being up in New Hampshire, we tend to add it in. We would also like to have our solvent have very low solubility in water, so we don't lose our solvent and don't contaminate our exiting water stream. And finally, obviously, we need to ensure good phase behavior. This includes good liquid-liquid equilibrium behavior in the extraction column and good vapor-liquid equilibrium behavior in our distillation column. In particular, we want to make sure our solvent doesn't form an azeotrope with furfural, otherwise we're not making much progress. So as I said in the beginning, the solvent selection process is fairly straightforward. In this particular example, we're starting with a database containing 653 solvents. Now some may say that there are thousands and thousands of solvents, but this problem is to select a solvent for an industrial process. We need a solvent that can be found at reasonable prices and is available in bulk quantities. We then apply our restricted groups constraints. Again, these are the groups we obtained from considering environmental constraints, reactivity constraints, and our good neighbor constraints. Applying these constraints removes 222 candidate solvents. So continuing our selection process, our database now contains 431 candidate solvents, and we now begin applying our physical property constraints. Applying our boiling point constraint eliminates 242 solvents, which leaves us with 189 candidate solvents. Applying our melting point constraint eliminates 24 additional solvents. And finally, imposing our water solubility constraint eliminates 77 solvents, giving us 88 solvents to examine further. At this point, we can apply our good phase equilibrium constraint, or in our case, we can just generate liquid-liquid equilibrium diagrams for each candidate solvent and select those that look promising. We can then continue to screen by generating vapor-liquid equilibrium diagrams for the most promising candidates. This screening process for good phase equilibrium behavior can be done by examining actual data, if we are very lucky, but is typically done using estimation techniques such as UNIFAC. Those solvents that had good phase equilibrium behavior would be recommended for experimental testing. For this particular example, we found several interesting candidate solvents, one of which is shown here, cyclopentyl methyl ether. It was of particular interest because this solvent had just recently been investigated for other reasons. Many of the final screening tasks still need to be done manually, searching for and understanding regulatory restrictions, compiling prices, availability and delivery dates, evaluating public perception, which is very important. We had once recommended diethylene glycol as a very good solvent for a certain application. Unfortunately, several weeks after we made that recommendation, there were news items in which diethylene glycol had been found as a contaminant in toothpaste. Even though our solvent application was not going to be one which would have human contact, it was decided not to be a chemical that the customer wanted to start using if it didn't have to. And finally, what we have found to be the most important step, repeating the entire process. Very often, only at the very end, only when we have seen the recommended candidates, do we have a good feeling of additional constraints we may need to impose, or a willingness to relax certain constraints. For example, we may want to relax our water solubility constraint, which might allow more oxygenated solvents to be selected. Oxygenated solvents, which might be more environmentally friendly. And this is really where a software tool is essential, repeating and refining the selection process over and over again. As I mentioned throughout my talk, the tasks needed to select solvents are fairly straightforward. However, hopefully as you saw in the example I've shown here, we are manipulating a tremendous amount of data. We're estimating many physical properties. We're imposing many different constraints on substructures, and we're constantly searching a database in various ways. Just the large amount of information that we're processing and the somewhat uncertain and even sometimes ambiguous information that we're processing means we may want to repeat this process over and over again. And at a minimum, a software tool must give us an opportunity to clearly document each of these revisions and each of the decisions we make. As a final thought, the tasks needed to select solvents are very well known, and we're constantly developing better rules and better physical property estimation techniques, and the software tools continue to advance. But we have found that organizing and documenting the large amount of data, calculations, and decisions used and developed during the selection process is actually the greatest benefit of using computational tools. So I hope that through this presentation I've been able to convey the approach we use to select solvents. If you have any questions or would just like to talk about solvent selection, physical properties, or chemical products, please contact me at my email shown here. Or during the conference, you can find me at the Molecular Knowledge Systems virtual booth. Thank you very much.